Okay, so this lesson is on thin film interference. It is a very interesting effect about the wave nature of light when you apply either a thin film to glass, or if you have a situation where there's a thin film of oil or soap or something like that on a surface. And what you'll get is the sort of a telltale interference pattern, and often even a rainbow effect will show up. And again, this is because you're getting interference happening for different thicknesses of the surface, as long as it's really thin. And what you'll notice is that with that interference, and it happens over different wavelengths. And so since it's constructive and destructive in different thicknesses for different wavelengths, you get an interference pattern that is offset from each other, and you end up with a rainbow effect. Much like what you would get with a double slit experiment, where you're sending in visible light, which has all different wavelengths in it, and the different wavelengths spread out differently. And because of that, you get a rainbow effect from that as well in the interference pattern. So it's very similar to that. So you'll often see something like this in a bubble. So in a bubble that has a thin film on it, you'll see here there's little interference bands. And depending on the wavelength of light, this is just using fluorescent light, you'll see that there's even some color variations. But due to the very, very thin film that's here, you're getting reflections of light off the top surface of the film, and then some transmits through and reflects off the bottom piece of the film. And what ends up happening is that you will get constructive or destructive interference of those reflecting waves. In areas where it's dark, there's destructive interference, and in areas where there's some color, you're going to see constructive interference, and you'll see the light. So you get this ring pattern because it's bright, dark, bright, dark, bright, dark, due to the constructive and destructive interference for the different thicknesses. In oil, it looks like this. So oil on top of water, or a thin film of oil, it's very pronounced, and when the light shines on top of it, it reflects off the top surface and off the bottom surface, and when the two interact, you get a very nice pattern. And again, it is in the rainbow because visible light coming in, it will interfere both constructively and destructively in different thicknesses of the oil, and therefore it will spread the light, much like the double slit interference situation, and you'll get the rainbow effect. Here's an example of a thin film that's being held vertically, and you can see it's dark up here. This film, gravity is pulling this film down. You'll see the light, dark, light, dark, light, dark, and the color variations due to this interference of different thicknesses. It turned black here because even over white light, it's so thin up here, and because the thickness is so incredibly thin, you get destructive interference for all wavelengths. And so the light is reflecting off the surface, but it's reflecting off the top and the back, and because the thickness is so thin, it's actually it's destructively interfering. So it's completely destructive interference due to the reflection here. Down here, you're getting these really nice colors, and again, there's different bands because those are the different orders of the reflection that you're seeing and the interference pattern that you get. Okay, well, let's look at the analysis of this and see, why do you get areas of destructive and constructive interference, and why is it that for reflectance you'll see that if the film is really, really, really thin, that you get all destructive interference and nothing reflects back. Even though there's light shining on it, there's none reflecting back, which means it's all transmitting through due to conservation of energy. That has to make sense. Alright, so let's take a look at the analysis and see just how simple it is to discover and figure out how it works. Okay, with thin film interference, we're going to look first at reflectance. So we're going to start with the reflectance type measurements. Now, we're going to look at three specific cases, and then we're going to extrapolate those three cases to all cases. The first one we're going to pick is when the thickness of the film, which is right here, is much, 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 much smaller than the wavelength in the film. Now, what we have to realize is that this lambda that you see here, this is the wavelength in the film, and we'll talk about that later. It's not the wavelength of the light that's shining in. The wavelength of the light when it goes into the material, remember if you're going from air into soap, for instance, the wavelength, because the speed will slow down but the frequency stays the same, the wavelength will get smaller. It will get smaller by the index of refraction of the soap, right? So we have to keep that in mind, that when we talk about this thickness, we're referring to the wavelength in the film, okay? And what we're going to see is we're going to indicate where phase changes occur. And a phase change is when the light reflects and inverts. So when the reflected ray is inverted, and remember that this happens whenever you go from a less dense optical medium to a more dense optical medium. So whenever you're going from air to a soap, for instance, where the end value of air is approximately 1 and the end value of soap is probably around 1.33, it's going from less dense to more dense, and so the reflected ray will be inverted. The transmitted ray always stays on the same side. If you refer back to our slinky activities, we always know that the transmitted wave is always stays the same shape, and the reflected wave will come back inverted if you go from more dense to less dense. If you go from more to less, more dense to less dense, you get no phase change. So there's no inversion happening. Okay, so that's a bit of quick review. And so now let's take a look at a situation. Now, for every instance here, we are talking about light that is normally incident on the material. So that when I say normally incident, okay, so the wave must be light is normally incident. So it's going to be normally incident on the material, okay? That means it's coming straight down, transmitting through, and doing the reflections. I can't draw that. It's very difficult to draw it, coming in, showing all the schematics. So in order to make this visible for us to do, we're going to draw it on a slight angle. But you got to remember that we're talking about light that is coming straight down, traveling in, reflecting off these two surfaces, and interfering with each other. I'm going to draw it on an angle simply because it's easier to see. The way I like to do this is if I show an incident ray coming in, we know it's a wave. So what I'm going to do is I'm going to show it as a crest. And so I'll do it like this. So a crest wave comes and is incident on the material. Now, what we're going to call this here is this is our thickness, T. Okay, so that little T there is the thickness of the film. So this is air to soap and then to air. And so from air to soap to air. Okay? Now, here's the situation. If the thickness is really, really, really thin, very, very thin compared to the wavelength, let's see what happens. Wave comes in, hits a boundary, it's less dense to more dense, so there's a phase change, there's a phase shift, which means that the reflected ray will come back as a trough. So the crest will turn into a trough. Okay? Now the transmitted wave, the wave that goes into it, I show it bending a little bit because it's going to refract. If it was a crest going in, it stays a crest coming out. So it goes in as a crest, travels through as a crest. Now, when it bounces off the back surface, when it reflects off the back surface, it stays a crest because there's no phase change. So here, this is called a pi phase change. And here, there is no phase change, which means if it's a crest, it stays a crest. Here, if it's a crest, it becomes a trough because there's a pi phase change. That's what it's called, pi phase change. Now, here's the important part. We're going to talk about a path difference, okay? The path difference here is approximately, so I'm going to call this path difference. And if you refer back to our other analyses, we've learned about what path difference does to interference and things like that. So here the path difference, the PD, is approximately 0. Because the thickness of this thing is so small compared to the wavelength, it's tiny. Like you imagine, I can't draw it small. That's otherwise the diagram's hard to do. It's extremely small. Now, if it was extremely small, what you would expect is that once it reflected off the top surface, it would barely travel at all, maybe just this tiny little bit here, and then reflect off the back surface. Well, if the reflection off the back surface, if it was a crest and stayed a crest, it would come back out still as a crest, because the thickness is so incredibly thin that there was a pi phase change at the top surface and no phase change at the bottom. And because it's so incredibly thick, you basically end up with a situation where a crest and a trough meet when they come out. Well, if for every instance a crest and a trough meet when they are coming out for this particular wavelength, you will get destructive interference, and the wave actually will not reflect. So we get destructive interference. Now, what we're going to also notice for in general is that the path difference, PD, is always equal to 2t. Okay, that's an important thing to remember. Now, since the thickness is so thin here, it's about 0. We're saying the thickness of this thing, I want to make it as close to 0 as possible. So why is the path difference 2t? Well, if the wave comes in and travels down, it must travel back. So if it travels down t, it must go back up t, and that means that you've got 2 times the distance of the thickness, which is t. So the path difference is 2t for all instances. In this case, our path difference was basically 0 because I made that thickness about 0. But for every case here, we're going to see that the path difference is double the thickness. Let's make the thickness a bit bigger and see what happens. Okay, so here, now I'm going to shine the ray in, and it's going to start as a crest. You can start as a trough, but I'll just keep it consistent, start it as a crest. If the crest comes in, what I'm going to say now is I'm going to make it very specific. I'm going to say that the thickness of this soap, in this case, is 1/4 of the wavelength of the light in the soap. Remember, it's in the soap. So the wavelength of light out here is a little bit, and in here, sorry, is a little bit smaller than the wavelength out there because the frequency stayed the same, but the speed slowed down. So what we're going to do is I'm going to make this thickness exactly 1/4 of a wavelength. So if the wavelength was 400 nanometers inside the soap, which means it was a little bit bigger out here, then 400 divided by 4 means that this would be a 100 nanometer thick soap bubble. Okay? And then there's air on the other side. Let's see what happens. Well, first of all, the path difference. The path difference in this case is twice the thickness, down, back. Well, that means that's 2 times lambda over 4, so it's a half of a wavelength. So the path difference here is one half of a wavelength. Okay? And another way of thinking about that is that the thickness is 1/4 of a wavelength. So the path difference is a half a wavelength. So when the transmitted wave goes in, it refracts, stays a crest. It bounces off the back surface as a crest because it's no phase change, right? Because we're going from more dense to less dense, so there's no phase change. Here it bounces, and because it's from air to soap, there's a pi phase change, like this. And now we got to think about this. It is a right now, sorry, it's a crest, okay? So when it's a crest, there was no phase change, so it reflects on the same side, so it stays a crest. Now here's the issue. It says here that we're the path difference, the wave has now moved a half of a wavelength from where it would have been. So if it went through as a crest, but now it's a half a wavelength offset because of the path difference, it will come out as a trough because now it's a half a wavelength behind. Well, now we have a trough and a trough meet, and this is constructive interference. So for a very, very thin film, you get destructive interference. And remember that video when it reflected back when it was super thin, it was all black. There was no reflectance. In the areas where you had the bright bands, the thickness was such that it was 1/4 of the wavelength. And so you got constructive interference. Okay? Well, let's see what happens now if we look at a case where the thickness is half of a wavelength. So now it's even thicker. So I've tried to show the diagram getting thicker with time. And so it comes in, it starts as a crest, there's a phase change. So it does that, it transmits through as a crest, bounces off, and you say, oh, soap to air, that simply stays a crest. And then what happens? Well, the path difference is the key. It's twice the thickness, because you got to go down and back up. Again, we're assuming normal incidence here. So it's 2 times lambda over 2, and you're 1 wavelength out of phase. Well, if it was a crest and coming back as a crest, but we're 1 wavelength ahead, or 1 wavelength, behind, 1 wavelength behind means that we've skipped a trough and we're back to a crest. Because it's not a half a wavelength or a half an interval out. And what does this mean? Crest and a trough meet, it's destructive. And so now you can see why the varying thicknesses of the oil or the film will produce destructive, constructive, and destructive interference, and so on and so forth for different varying thicknesses. So if the bubble's not uniform in thickness, what you'll end up with is that, or like that gravity one where it was hanging, for really, really thin pieces, there's completely destructive and you don't see anything. But as the thickness got thicker, you saw the bands show up. It went from destructive to constructive and then back to destructive, back to constructive, because the thickness was getting thicker and thicker over time, and it kept alternating from constructive to destructive to constructive to destructive, following the path difference. Whenever the path difference is half the wavelength, it was constructive. Whenever the path difference was 0 or lambda, or like 1 wavelength out, it was destructive. So you can summarize this really nicely, and it's like this. Whenever the thickness is a 1/4 of a wavelength, 3/4 of a wavelength, 5/4 of a wavelength, so on and so forth, or when the path difference is half a wavelength or 3/2 of a wavelength, etc., just following the 2t rule, just multiply this by 2, what you'll notice is you will always get constructive interference. For destructive interference, that will happen when the thickness is 0, when it's lambda over 2, when it's lambda, 3/2 lambda, so on and so forth, or when the path difference is 0, lambda, 2 lambda, 3 lambda, etc. We're going to do an example of this in a bit and see how you can use this to figure it out. So it's a quantum mechanical effect. It's really, it's a wave nature of light effect, which is quite impressive. It's used for anti-reflection coatings. It's used on glasses, for fighter jets, goggles, all kinds of things use this, and it's used all the time. And you see this effect in lots and lots of places. Oil spills just being one of them, but soap bubbles are the other one, or just blowing bubbles outside, in the air, and you'll see all the colors swirl around and all the interference patterns that show up from it. It's because of this varying thickness of the bubble itself. and the interference of light as it bounces off the back and front and back surface of the surface of the bubble or the film. Okay, that was for reflectance. Let's look at the opposite if the light's on the other side. So what if the light is, if you're looking through a soap bubble and the light is coming through and passes right through, what do you see on the other side? We just showed on the previous side what happens when we're looking at the reflectance of the light. But what if you were, so that's if you shone the light on it and you were standing here and looking at it, what you see reflected, like a soap bubble and things like that. What does the person on the other side of the soap bubble or the person inside the soap bubble or on the other side of the film see? Like, so if you're wearing glasses that have an anti-reflection coating on them, like some kind of thin film, people on the outside will see the purplish blue tinge of the glasses. You don't see that on the inside. When you're looking through the glasses, you see something completely different. And that's the whole point of getting these thin films on those glasses or on these goggles. It's so important. Okay, so let's look at the cases, the same cases as before. We're going to look at, when the thickness is really, really, really small, and we're going to look at the cases when it gets a bit thicker over time and see what happens. Okay, so in the first case, when the thickness, so this is the T, and the thickness right here. So what happens when the thickness is approximately 0, which means that the path difference, which is 2T, is approximately 0. Okay, so it's super, 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 super thin. But now we're looking at the transmitted ray. Well, here's what happens. The ray comes in, bam. It refracts, bam. And then it transmits again. Nothing strange there. The wave just goes doo-doo-doo. And if it was a crest, it stays a crest the whole way. Now, this one bounces off the back. When it bounces off the back, it went from soap to air, so it didn't invert. Then it bounces again, and it went from soap to air, so it stays a crest. And it transmits and that's what we got to figure out. All we care about at this point is from here up to here, there. So that's the path difference. Well, if there is no path difference, that means that if there's no path difference whatsoever, and this is a crest, then it stays a crest. And so now we've got it's constructive. Now what's interesting is that for the reflected part, if I did this in a different color or pencil or something like that, you would see that obviously this was a trough, this was a crest, and we had destructive at the top. Well, it makes sense that if it was destructively interfering this way, none of the energy was coming back. It was all being destructively interfered, which means that it had to be constructive on the other side. Otherwise, the energy's gone. And you're not just sending light in, it disappears. It didn't get absorbed. It all transmitted rather than being reflected. There was no reflection, all transmission. This is a very typical case of a thin film sort of a situation with an anti-reflection coating. So in that soap bubble that we saw at the beginning, where it got really black at the top as it got super, super thin, it's because all the light that was hitting it was reflecting but destructively interfering, which means that it all was coming back and constructively interfering on the other side. So it was 100% transmission through that thin film. All right, let's take a look now when it gets thicker. Now, if you remember from last time, it went destructive, constructive, destructive for reflectance. What do you think is going to happen? You probably guessed it, constructive, destructive, constructive. It's going to be the opposite, which just intuitively makes sense. So for this one, we're going to make it a bit thicker. You can see from the diagram it's a bit thicker. The path difference is 2t. So we've got 2 times lambda over 4, which is half of a wavelength. So now our path difference is half a wavelength. So light comes in as a crest, transmits through as a crest, transmits again out as a crest, bounces here, more dense to less dense, stays a crest, more dense to less dense, stays a crest, You have to talk yourself through it. Now you're half a wavelength out. Our path difference is half a wavelength, so we're in a situation where out pops instead of a crest, out comes a trough, and we get destructive. Exactly as we expected. It has to, otherwise, I mean, conservation of energy doesn't work. If that doesn't happen, then all bets are off. Okay, for the last one, you get the idea. I think this analysis, you're probably almost capable of doing it yourself at this point. It's 2t, 2 times lambda over 2. Oh, look, back to one wavelength path difference, not thickness, that's path difference. So we go boom, draw that. So the transmission's easy, it comes out, it always transmits as whatever it started as. Then it reflects, there's no phase change. Now because we're a wavelength behind, because we've been lagging behind by exactly one wavelength, it means that we're just at a crest previous to that, or sorry, after it. And so it comes back out like that. And that's constructive. And what you will clearly see is that when the thickness, for constructive interference, you get it when the thickness is 0, lambda over 2. This is for transmission. And 3 lambda over 2, etc. Or when the path difference is 0, pi, 2 pi, 3 pi, etc. And for the other one, it's for thicknesses of 1/4, 3/4, 5/4 of a wavelength, or when the path difference is 1/2 a wavelength, 3/2 of a wavelength, 5/2 of a wavelength, so on and so forth, you will get destructive. How does this compare for the reflectance? It is the opposite. And clearly that makes sense. Conservation of energy says that that would be the case. You can't have a destructive interfere on both sides, like the light would be gone. Which I guess you can get, possibly. Okay, very important nuance to all of this. And we'll look at an applet that shows this. Highlight this, I don't know how you want to do it, but this is so important. And I've mentioned this before, is that in all cases, the wavelength we're talking about is the wavelength in the film. Now remember, to find the index of refraction of a film, what you would simply do is you need to take the speed of light and divide it by the speed of the light inside the film. So C is equal to F lambda, and the speed inside the film is F lambda film. And so since the frequencies are constant between the two of them, remember the frequency doesn't change. So the wavelengths, if you are going from less dense to more dense, if the speed has to slow down, then that means that the wavelength must get smaller. And so when the frequencies divide out and you rearrange for lambda film, you get it's the wavelength in the air or the first material, and the divided by the wavelength, sorry, the original wavelength of the light divided by the wavelength in the film. Okay, so it's that's simple to figure out, and we'll see how we're going to use that. This is like super, super, super important. Otherwise, it doesn't make sense. Okay, an anti-reflection coating is pretty cool. Like they put these on glasses, they put it on aircraft so that radar is absorbed. And so, for instance, for the glass situation, a single layer coating, what you would see is that they're going to apply a thin film on top of the glass, and then they're going to get it to, for a very specific, it only does this over very specific wavelengths. They have to put different types of materials on so they can go over a range of wavelengths. That's a lot more complicated. That's in the second example there. We're just going to look at the basic case. So let's say that a light ray comes in. Again, it's normally incident, not this angled stuff. It transmits through as like this. Now, because air, this film is going to be denser than air, so it's going to reflect as a trough. And the glass, it turns out, is also more dense. So here, the N of the air is less than N1, which is less than the glass. It's important that this glass is more dense than this one, And what happens is there's another phase change. So here you're going to get, in this instance, here you get a pi phase change, and here you get a pi phase change. Now, if you are at a thickness, here it's important, if you're at a thickness of a quarter of a wavelength, that's what we want. We want a quarter of a wavelength thickness because the path difference, we need, if this is a trough and this is a trough, then in order to get destructive interference, because right now if that comes out as a trough, we're getting constructive interference, and we don't want that. We want destructive interference. So the only way we can get destructive interference is if that happens. And the only way we can get that to happen is if the path difference is half a wavelength. This must be the case for destructive. So what they do is they know they need because there's going to be a phase change here and a phase change here, they know they need this situation to happen, which is the fact that you see here. So what they have to do is pick the non-zero case. They can't put they can't put a zero phase, like a infinitely thin coating on that. It's actually very difficult to do. So what they do is they go to a quarter of the wavelength of the material of the light inside here, and they know it'll be out of phase by half a wavelength, and therefore you'll get destructive interference. Well, what that means is that if it's destructively interfering in the reflection side, all of the light is going through. So the people that are looking through the glasses with their eyes here, right? So here's their eyes, and they're looking at the glass. They're going to get all the light coming through. People over here will not see any reflection of the light, so it's very clear. And these people get all of the light transmitting through, and they don't get any of that glare, and they don't get a loss of light due to that reflection. As I pointed out, it's a lot more complicated. This only works for one wavelength of light, and so they'll often pick certain, like there's like blue filters now that they use, which are important. And so if they want it over a wider range of wavelengths, they use multiple coatings. This gets quite complex, so we're not going to do the analysis here. But in this case, you can get different coating lengths so that more wavelengths are destructively interfering on this side, which means that they're constructively interfering behind. Okay, so to do an example, you could look at something like this, where I'll do the one example and then show you the after. So in the summer months, an amount of solar energy entering a house should be minimized. Okay, sure. Window glass is made very high efficient by applying a coating to maximize reflected light. So you want all of the light to reflect off your windows instead of come through your windows, so that you can, like, you know, in the summers, it's just something that you want to do. Lots of windows, if they're really high-end windows, will have anti-reflection coatings on them in very specific thicknesses and made out of very specific materials to reflect certain types of light. So light in the mid-range of the visible spectrum, so we're just going to pick about 568 nanometers, travels into a window glass. 1.5 is the index of refraction. What thickness of the added coating, so here's the index of refraction for the coating, is needed to maximize reflected light and minimize transmitted light? There's the answer. So what we do is make a quick sketch. So there we go. And we're saying, what is the thickness required? Here, the n is 1. Here, the n is 1.4. And then the glass is 1.5. So this over here is the glass. This is the film, and this is the air. Okay, shine the light. Light comes in, hits. Let's send it in as a crest just to keep it consistent. It reflects, transmits as a, like this. This is a phase change, right? So here we have a pi phase change, and since we're going from less dense to more dense, we're going to get a pi phase change there as well. Now, if we want on this side, I know it says we want to maximize, so we want constructive interference on this side. The only way we can get constructive interference on this side is if a trough pops out. Okay, well, and oh sorry, there was a pi phase change here as well. So if we need a trough to pop out because of this phi, in order to get constructive interference and maximize it, here's what happens. The path difference, remember, is always twice the thickness, there and back. The only way, if this is inverted, the only path difference that would give you a crest staying a crest is if it's 0, lambda, 2 lambda, etc. If there's no path difference and it turned into a trough, it'll stay a trough. If it's a wavelength behind, it'll start as a trough, end as a trough. If it's 2, so on and so forth. So what does this mean? Well, simply, if 2t, now it wants what thickness of the added coating. We're going to assume that we're not going to pick 0 because that doesn't make sense. We're going to look for the minimum thickness. So 2t must equal lambda. We're going to pick this one here, the non-zero case. That would be the minimum thickness. Let's go for minimum thickness, okay? Because we're looking for minimum t. And that thickness would be lambda over 2. Okay? And we can't solve it because we don't know the wavelength in the film. Remember, this is all about the film. So the thickness would be something divided by 2. Well, the wavelength in the film is simply the normal wavelength divided by the index of the film. So it's 568 nanometers, and then in the film, because the film had this index of refraction, it reduces down because the speed slowed down but the frequency stayed the same to about 405.7 nanometers. So we plug that in. Which does not match that, and that's because that is not right. There you go. So that answer was wrong. The other ones in the problems are good, but that one is actually a mistake. So it should be a 203 nanometer thickness in order to get that result. Okay, quickly to show you an applet, and then you can work on the rest of the problems following that very similar analysis. The applet is like this, for instance. And I don't know if this is helpful or not, but it might be. So I'm sending in a wave of 600 nanometers. You can see it up here. Here's the wave coming in. It's 600 nanometers, okay? The material on the one side of the film here, this is the one side of the film, is air. It's 1. The film inside here is 1.33. I just made it water. And then the film on this side, or soap, the film on the other side is 1. So this is just air to soap to air. Now, we know that to get destructive interference for this, this is the combination. So this is the reflected wave here off the front surface. This is the reflected wave off the back surface. And this is the resultant. This wave and this wave interact and give this wave. If I increase the thickness, watch what happens. Bam, there's destructive interference. Then it's constructive, destructive, constructive there, and destructive there, constructive, destructive. Now, if the film gets too thick, there's so many reflections occurring within the material that you lose all interference effects. And once the thickness is too big, all the interference effects are gone. So it has to be really, really thin, on the order of the size of the wavelengths. So can we predict where these were? Well, let's find the first one. There we go. There's the first one at 226 thickness. So if the wavelength coming in was 600, right? And we know that for reflectance, the first destructive interference, other than 0, should be when the path difference, or when the thickness is a quarter of the wavelength. So if you remember back, a quarter of the wavelength. So we take 600, divided by 1.33. So the wavelength of the light inside the material is 451.1 nanometers. It's gotten smaller. So it says that at a thickness of a quarter, so if I divide that by 4, you should get, if I divide it by 2, so 600 divided by 1.33 is 451.1. To get it says, other than 0 path difference, when your path difference is a wavelength, or when the thickness is half of a wavelength, so divided by 2 is 226. That's what my calculator gave, and that's what this gives. So 226. So it works perfectly, and it shows that. The 112 that I did, 112.8 should be completely, so about 113 should be completely constructive. And it is, in fact, completely constructive. You get maximum construction because the reflected wave and this wave, they come back out in phase. So this applet, if you can figure it out and sort of follow it, you will see that it completely corresponds with the analysis that we just did. This may be a bit too much in terms of a little confusing to use for you, but it is very, very accurate and helpful for understanding this analysis. Okay, that's about it. Work on those problems, and we'll continue with it in class.